right, so moving on to light. Again, this is a picture of Crater Lake. It's one of the deepest, clearest lakes we have. And so light is going to penetrate much farther down than in a lake that's what we call turbid or cloudy or murky, right? So you can calculate these light profiles versus depth. This is how these figures often are, with depth at the 0 at the top and going down. It's kind of a nice way to visualize changes with depth. But we have to understand, how does light even get into these systems? So before even entering the water, sunlight can be reflected back to space from the atmosphere. It can be absorbed or scattered by atmospheric particles, can be reflected by clouds. It can be reflected by the surface of the water or snow. The light is usually transmitted, not reflected, by clear ice. So ice can allow light to penetrate through. But then once it's in the water, the light that makes it to the surface of the water can then be scattered by the water itself or suspended materials in the water. It can be absorbed by the water. It can be absorbed by dissolved materials, particulate materials, bottom sediments. It can be backscattered to the surface. And so all of these things can happen. So just getting the light into the water is challenging enough. And then it kind of attenuates, which means it diminishes as it goes down through the surface of the water. So there's not much light available for photosynthesis at depth. Okay, lots of stuff can happen to light before it gets down into the deep parts of a lake. Here you can see the different wavelengths of light. This is the visible spectrum of light, and on the red side we go into the infrared. On the purple side we go into the ultraviolet and the X-ray side. So you can see that the spectral energy distribution of solar radiation outside the atmosphere versus inside the atmosphere at sea level, you can see the difference in how much available light energy is coming in, and that most of the energy that makes it to the surface of the earth is in the visible light spectrum, which is good news for plants and things, but not all of that makes it through water. Okay, so light attenuation is this concept that light intensity decreases logarithmically with depth. So light won't be transmitted as far, especially if there are dissolved compounds like humic substances in the lake, if it's a productive algae-rich lake, or if there's suspended materials like silt in the water, okay? So here you can see light attenuation for, and I'll talk about what these terms mean. Oligotrophic is a very nutrient-poor system, okay, very clear blue water. Mesotrophic systems have a little bit more nutrient and more productivity, and eutrophic systems are like green gunky systems, lots of life and green algae and stuff, but not very nice clear water, okay? So the amount of light, the percent of incoming light let's see, this is on a normal scale, and this is on a logarithmic scale. So you can see these kind of curvy trends which become linearized when you use a logarithmic scale. That's the nice thing about logarithmic scales, is they can help us see patterns. Okay, you can calculate this attenuation coefficient. It's called eta, this little kind of N looking thing. And by taking the natural log of the light intensity at 0.1 minus the light intensity at 0.2, so this could be the surface versus 10 meters or 20 meters, and the depth at 0.1 and 0.2. I don't know if I got those backwards. I hope I didn't. I hope that's correct. We'll double check that, okay? And you can also calculate the percentage of transmission. It must be right because it's the same way here. Would be 100 times the intensity at 0.2 divided by the intensity at 0.1 times, again, the distance between the 2 points. So we're going to work these calculations through in workshop as well. All right, so we can use what's called a Secchi disk or a Secchi disk to measure light penetration in a lake. And what you'll see is that the extinction coefficient, basically how much light is lost, how rapidly, is very steep for an oligotrophic lake, and then it's very shallow for a eutrophic lake. So I think this is a little confusing, but basically this is how it works. So you take this disc, it's a black and white disc usually, sometimes it's just white, and you lower it down a column down into the water. Someone's lowering it while someone else is watching, usually laying flat on the deck, you know, with something covering your head to get rid of the glare. And you watch as it's lowered all the way down, and then you tell the person, okay, I can't see it anymore. And then they keep lowering it a little bit further, and then they start raising it back up, and then you tell them when you can see it again. So you get 2 measurements of Secchi disc depth each time you make this measurement. And it helps you understand basically how clear the water is. You can also measure things like turbidity and total dissolved solids to get at water clarity. So it's really important measure because it tells you the depth that productivity can take place. Basically, if light can penetrate and you can see something, that means that algae could be living there photosynthesizing. And so here's some pictures of Lake Tahoe and different wavelengths of light and their attenuation curves. You can see most of these wavelengths are generally logarithmic, but you can see that the red and orange light is lost much faster than the blue light. And this is partly why Lake Tahoe and Crater Lake are so blue when you look at them. You can also see that the distance, the Secchi distance, has changed considerably over time. So unfortunately for Lake Tahoe, it's losing water clarity. And they think that it's partly because of phosphorus additions when, you know, people who are going skiing there drive on the roads and grind the gravel that they put, you know, the stuff they put down for traction in the snow into dust. That releases a lot of phosphorus, and that dust then gets into the lake and has reduced visibility in the lake over time. So luckily, you know, things have gotten better a little bit, or they've basically stabilized over time. So this is just an update. This one was until 04, and then this one is showing that maybe we're losing a little bit of clarity again. Or, oh no, actually this is good. It's going, sorry, I got it backwards, right? So the Secchi disc is going back down. So we're gaining clarity again, which is great.